Hi, Damien. Hi, Alvin. Hi, Luca. Hi, Toby. Hi, Jonathan. Hi, Matthew. Hello, Rafe. Hello, everyone who's already here. We're just going to leave it 1 more minute for any extra people to arrive. Fantastic turnout.
It is.
Okay, we're going to make a start. So welcome, everyone. Thank you for attending this FINS webinar on MVHR do's and don'ts. I'll just start with a bit of housekeeping. You'll notice that you're all muted. If you have questions during the seminar, if you could please just put them in the chat, and then we will get you to ask your question at the end of the webinar, and Grant will answer it for you then. This session is being recorded, and we will make that available for people who weren't able to attend. So just a quick introduction to FINS and to myself. So my name is Jessica Ayres. I'm on the board of the Passive House Institute New Zealand. And for those who are not familiar with us, we are Te Toputanga o Te Whare Koru ki Aotearoa, and we advocate for health and well-being of New Zealanders in buildings, and we aim to address the challenge of climate change by drastically reducing operational energy in buildings. It's my pleasure to introduce Grant Henderson, who I've known for about 12 years now. And he is a certified passive house consultant, and he is one of the go-to people for certified passive house ventilation systems and the expertise of those systems in New Zealand. And I've seen him give presentations on this topic to builders over the last 2 or 3 years. And every time I see it, I get something new and valuable out of it. Therefore, I'll hand over to you, Grant, and I look forward to everybody's questions afterwards. Thanks.
Thank you very much, Jessica. That's a very generous intro, and thanks to everybody for attending today. As mentioned, I've been in the industry now for a while, about 13 odd years. I'm currently with Stiebel Altron. I've been with that company now for 3 years. And prior to that, I was with Fantech doing the Zenda heat recovery ventilation solutions as well. And when I first started with Fantech, I came across the first passive house that was being built in New Zealand, and that raised my curiosity. And here I am 13 years later, the curiosity got the better of me. So what I'm going to do today is share my screen. I'm going to do this in the right order. Share. Can everybody see my screen? No. I'm going to try that again. My apologies.
We could see the presentation, Grant, but we couldn't see it in slideshow mode. There, that's perfect.
There we go. That's better. Rightio. So I'm just going to move a couple of things around here so I can see myself. So during the initial years when I first started with Fantech, we were exposed to these new projects. Nobody in New Zealand really knew much about heat recovery ventilation. So we had to kind of feel our way around. And so what I'm going to do today is kind of share with you some of the things that we discovered through the years so that you don't have to go through that same learning curve. Some of the original projects had significant problems that had to be literally uninstalled and reinstalled. And but as time goes by, obviously we make more and more observations. So we just keep getting better at it. So today's presentation is really around the practical do's and don'ts of designing and installing a system. It's not really a sales pitch on the benefits of heat recovery ventilation and why you should do it. That's not what this is about. This is really more for architects and designers who are interested in incorporating these systems into their builds, and for builders that are installing them and the likes, and maybe any homeowners that are considering doing this for their own projects as well. We do quite a few self-installs, so we do provide a lot of technical support to individuals as well. Practical guide to heat recovery ventilation design and installation, and it's really got a focus on minimizing the negative or the potential for negative impacts. So we're going to talk a little bit about installed efficiency, true installed efficiency. So there's a topic there is when you get a brochure or a spec sheet of a heat recovery ventilation unit, it has a number which you know, we all gravitate to. How efficient is it? But as you'll see through the course of this presentation, that the true installed efficiency is a different subject, and there are ways of minimizing your losses through installed efficiency. Sound levels are always a problem, and they continue to be a problem. So good advice on where to locate your grills and the likes, and not to do that. And avoiding unwanted losses and gains. So there was News Talk ZB actually had an interview this morning about homes that are overheating, and that actually is our biggest concern. So these high performance homes are incredibly easy to heat, but they are not very easy to cool down. That's a lot more complex. So there's a couple of ways that we can avoid unwanted gains through the ventilation system as well. We'll go through that. And as you'll see through the course of this presentation, it's always about minimizing the potential for negative influences. So we're going to tame sound problems, and we're going to improve true installed efficiency, and then we're going to talk through ventilation design. We'll start with that of ventilation design. What are some of the things that we're considering along the way? So I'll just kind of run through it and talk, you know, think out loud basically as I go through that, and then some of the components that we're going to be using and why. So we always start off with receiving a set of plans, and it's not very complex at the initial stages. Selected a project here, which is very simple, single level, 3-bedroom dwelling. It's got 2 bathrooms, a kitchen, and it also has a laundry, but the laundry is in the garage, which is outside the thermal envelope. So we're going to exclude that from the ventilation design. The initial process is to identify living spaces, and that's bedrooms and living rooms. This is where we're going to flush fresh air into those spaces 24 hours a day, 7 days a week, all of the time. And then we identify the wet rooms, and that's where we're going to extract air out of those locations all of the time. The amount of air going in is the same volume of air that's going out. So we're not pressurizing the home, and we're not depressurizing it either. So no air is being forced through the fabric of the building in any way whatsoever. The leftover spaces are just air transfer zones, and there's no grill there, so there's no supply air grill and there's no return air grill. It's just simply an area where air overflows into that space and makes its way down to the wet rooms. So on this particular project, most of it's fairly straightforward, but I believe you can see my mouse. So I'm just going to indicate this walk-in wardrobe here on the corner, and it's the kind of thing that we would have a discussion about. One, it's large enough to actually justify ventilating, but typically when there's an ensuite, there's only 1 door, but on this project, it's got 2. So we can't rely on the return air volumes of that bathroom to just pull air through that walk-in wardrobe. It's highly likely it will, just looking at the layout. So it's not a big concern for us at this stage. And but what we are considering when we're looking at the things like this is that this bottom corner here is a geometric thermal bridge. You'll I've seen the names of the people in the room. You'll all know what that is. But basically, that's a cool corner on the inside. And what we have in walk-in wardrobes is that, all the clothing and the likes tends to reduce how the air moves through that space. So if that project, if this walk-in wardrobe was on the other side of the building, this is the west side and this is the southern side. So if it was on the eastern side, southeastern side, that might be a situation where we'd say, well, maybe we should ventilate that space just to make sure that the no mold is going to grow on any shoes or clothing. Once we identify those spaces and how much space we've got or volume we've got, we simply just run it all out on a spreadsheet and work out how much air do we need to deliver into the space to achieve an air exchange rate of around about 0.35 to something a bit higher, maybe up to 0.5, depending on the location. I'd have to say that areas that are more humid, like Auckland, 0.5 air changes seems to be a much better number. And for areas like Central Otago, where you have very cold winters, 0.35 is a pretty good number. But what does trump everything in these situations is the number of occupants. And councils will basically, one, they won't really raise that question, but two, the allocation of occupancy for a dwelling is that the master bedroom is 2 people and every other bedroom thereafter is 1 more. So we've got a 3-bedroom house, so we're going to assume it's 4 people. This volume of air we've got up here for the wet rooms. So we've got kitchen, bathrooms. This volume is actually code minimum. So on this particular project, we've just gone straight for the lowest volume of air can we pass through those bathrooms and kitchen and toilet to meet code minimum, so that it will just go straight through council. So in this case, it was 130 cubic meters of air per hour for return air. And coincidentally, that's actually 0.4 air changes. So that's quite nice. We're just going to stick with that. And as you can see down the bottom here, it's also enough for 4.3 people. So unless we knew what the occupancy was going to be and it was higher than that, if we did know that, then we would have to adjust those volumes. So for example, if we knew 6 people were going to be living in this house, we would have to change that to 180 cubic meters of air per hour. Otherwise, it just won't be enough. It won't be enough air to remove the amount of moisture they generate on a daily basis. If we get it right, here's some real world evidence stolen from the Passive House Academy off my slides for the Passive House Designers course. A comparison between a airtight passive house, blower door tested at 0.6 air changes, just made it through, and another house in Auckland that was blower door tested, a new build, which was 5.3. Both have 4 occupants and both have 3 bedrooms. And as we can see, the red line down the bottom is the passive house, which is a lot more airtight and has mechanical ventilation, and the CO2 levels remain well below 1,000 all of the time, and the other house does not. So good evidence that natural infiltration is not a solution for ventilation. So 0.4 air changes is a positive and a measurable outcome, and it's been proven in the real world. So on the project that we've got, we've been, oh, my apologies, I've jumped one slide, with the intention of injecting fresh air into the living rooms, the bedrooms and the living spaces, and extracting air from the wet rooms. What we have there is that the wet rooms, the implications of that is that the wet room is a continuous extract air zone or a negative pressure zone. So that means that not only is the air being exhausted to the outside, but what it really means is that the moisture in that location is never given an opportunity to permeate into the rest of the dwelling. And so therefore it's actually looking after the fabric of the building, not just, exhausting air outside. We're bringing fresh air in, so indoor air quality is always better than outdoors. That's a term I heard from Jason Quinn, so I stole it. And the wet rooms are permanently negative pressure, so moisture never gets a chance to permeate to the rest of the dwelling. In this project, we were given a location for a heat recovery ventilation unit, and you can see it on here. It's in the center of the dwelling, so it's centrally located, which is fantastic. And then from there, we really, now that we know the volumes, we know how many tubes we're going to have to run through the place, and we now have a location. What we need to come up with is, a sensible suggestion of a system. And so what we've come up with on this particular project is we're going to fill up that cupboard with a ventilation unit, and we're going to distribute via small diameter plastic tubes, which are built specifically for ventilation, so they're not just some plastic product taken from somewhere else. So this is a visual reference for what it's going to take. There's a bird's eye view, and we can see that there's a concern with some overhang. We can't quite squeeze everything inside this space, so we're going to have a conversation with the architect later on today. And but other than that, it's fairly straightforward. The suggestion on this project is to just go straight out through roof for the outdoor air and the exhaust air. And one of the reasons for that is that it's about a 4-meter run to the external soffit, which is also not very big. So as you'll see later on in the slides, the length of the pipes that run to the external impact on true installed efficiency. So we want to keep that as short as they possibly can be. And that's why we've elected to just go straight out through roof. It's just a suggestion. So these designs or these layouts are really intended as a conversation starter. They're more for, to say, well, hey, look, this is what it'll look like. This is how much space it'll take up. Can we work through this and make it, easy for you on site instead of just, turning up on the day and trying to figure it all out then. So in this particular case, we're suggesting that we're going to use a Stiebel Eltron LWZ180 unit, and we're going to place a SDA noise attenuator directly on top of it, which is the box you can see up here. That is actually a noise attenuator. It attenuates all 4 sides, so both internal and both external grills. And the rocket launchers you can see on the side there is where all the plastic tubes will connect. So from a bird's eye view, it's going to look something like that. With the Zender system, they do a different approach. They have the noise attenuators vertically mounted typically, but all of these noise attenuators, all of these remote model noise attenuators can be fitted anywhere. So you can actually put them anywhere in the dwelling, but Zender do have some brackets, so you can place this right down on it, on top of the unit, and then all of your tubes would come in from above. But a word to be aware of is that it wouldn't actually look like this. The noise attenuator would be right down on top of the unit. You would then bring the unit up on the wall as high as is practical. But because the tubes are coming out of a services cavity, they need to make a nice, smooth, gradual bend. And so you really want the top of the noise attenuator to be around about 400 or 500 millimeters below the finished ceiling line, just so that you can complete a nice, smooth, gradual bend to come down and make the connection into the top of those noise attenuators. And so it's a great photo for marketing, but it's not how an install would look. When selecting a unit, we're always looking for one that will run around about half speed or maybe a little bit more. And that's when it's in nominal duty. So that's what it's doing all of the time, not boost volume. So that leaves some in reserve for that boost volume, but there's a few reasons why we do this, and I'll just run through those. So one of the things we look at is power consumption. So to meet Passive House certification standards, they look at how much power does it consume per cubic meter of air that this ventilation unit delivers. And so what we've got here is we've got 3 different ventilation units. So that's why you can see 3 different lines, but they're all behaving the same way. On the y-axis here, we've got the watts that's consumed per cubic meter of air being delivered. And as you can see, as the fan speed goes up along this graph, the amount of power that it uses per cubic meter of air goes up as well. So it's a good idea to be running the unit at a lower speed, just so you're kind of in that sweet spot anyway. It consumes less power. The second one is the heat recovery level. And as you can see on this graph, we have, efficiency on the y-axis, and we have the air volumes along the bottom. As the air volumes go up, the efficiency comes down. And that's the same for all ventilation units. But the interesting thing on this graph is that these dotted lines are the same ventilation units, but it's when there's condensation being formed inside the heat exchanger core. So when there's condensation inside the core, it's wet, and therefore it is more efficient at transferring energy. So it recovers more heat the colder it gets outside. So it just keeps getting better. The other one is obviously, and we all know this, so don't have to explain it too much, but basically the higher a fan is spinning, the more noise it makes. And so we want to run it at a lower speed just for that reason alone. Any sound that's created inside a duct can have a significant impact on what comes out the other end. If anybody's experimented as a child, just talking into a hose or anything like that, a small volume of sound into one end of a tube will actually become a focused reverberating noise at the other end. So we always want to make sure we've got noise attenuators directly after the ventilation unit, and that's as to acoustically separate the ventilation unit from the living rooms. So for all modern builds, that's an absolute must. That's why most of the noise attenuators you see are both. They're a noise attenuator and a distribution manifold for those small diameter tubes. After the noise attenuator, well, outside of the noise attenuator side of it, we've also got to deal with the external grills. And so they're a sound source as well. So my recommendation is that you should avoid putting an external grill near an entranceway, as sound will be, coming out of it. One of the first passive houses I visited, I think it was the second passive house built in New Zealand. I got out of the car and the external grill was pointing directly at where I parked, and I was quite shocked at how loud it was. So unless you can put additional attenuation between the unit and the external grill, keep them well away from outdoor living areas. And also don't point them at your neighbours' outdoor living areas as well, as we've had that in the past also. And it does come up a couple of times. External grill pointing directly at your neighbour's barbecue area, and you put it into the bathroom boost mode, and you get a couple of complaints from your neighbour. It can be fixed, but if we just avoid those locations, then we're dialing back some of the problems that we encounter with some of these systems. And what this entire presentation is actually about just minimizing the impacts of everything, and then we have a better outcome for everyone. External grills, there's not much explanation here. There's wall grills, there's through roof, and there's some combined units for where there's space issues. Not a lot to say, but some people do like to use their own grills, and that's absolutely fine. Some of the more grand design projects where you don't want to see external grills on, say, nice schist stone work or something like that, then custom work can be done, and that has been done in some other projects, like building, steel boxes and the like, so that it's hidden or concealed. And on that subject, if you are going to swap out for other grills, this project here was in Wellington, and it was probably the worst I've ever seen. Was when a architect swapped out the external grills that were specified and wanted to use something that was smaller and more attractive. And what we can see on the left-hand image of this one here is that the top part of the grill face is actually completely closed off. It doesn't actually allow any air to move through. And the unfortunate outcome for the local insect community was that the velocity of the air now passing through was so high that they couldn't escape. So basically they just perished and stacked up until, as you can see on the right-hand side, literally almost no air was passing through that grill whatsoever. So if you are choosing, custom grills or choosing another product, just remember that everything in the designs are all modular components, so they're intended to go together. But if you're going to step outside that, then maybe just engage someone like myself or your own designer and just run it by them. But the general rule of thumb is that the open face should be at least equal, if not more. So looking at external grill locations, they always need to be as close to the heat recovery ventilation unit as they possibly can be, as is practical. So, it doesn't have to be right next to it, but the ideal scenario would be that the pipe connection from the ventilation unit to the external grill would be around about 1 meter or even less, especially if there's noise attenuation involved. As the external grills, we don't want them to be noisy. Avoid entranceways and avoid outdoor living areas, and also avoid your neighbour's outdoor living area. But also never ever draw air from the western side of the building. What we've experienced through the years is overheating. Overheating is probably the biggest concern with high performance builds in my experience, and just avoiding anything that brings in unwanted gains. And drawing air off the western side is probably the worst of them all. That's cladding becomes sunbaked. It gets very hot. If you measure the temperature of cladding in direct sunlight, it can be as hot as 55 degrees. And then the air just literally just passes up the cladding and gets sucked into the grill. So on a warm summer's afternoon when the sun's low, you want cooler air, but you're actually getting hot air. The use of expanded polypropylene pipes in ventilation is highly recommended. They are expensive, so I can understand why some people want to, explore other options or even use flexible ducting. But what these pipes are is everything that you basically need. They're vapor proof, they're smooth lined, they are modular, they just press together. The intention is that they are airtight just by pressing them together. You don't require tape. There's many projects we visit where somebody has for many hours placed tape all around all the collars and the likes. It's not necessary. There are actually seals on the inside of the joiners, and there's also a flange where everything sits square and is abated. So they are airtight as long as they are square and fitted properly. So the intention of these is they are 15 millimeters thick, and being expanded polypropylene, it is an insulating material. But really the intention of that insulation is not to eliminate energy losses or gains in some cases, but it's really around reducing condensation forming on those pipes, because if we're bringing cold air in from the outside, that pipe will become cooler, and we're bringing it into a nice warm passive house. So warm air on a cold surface condenses. And some of the early projects that we experienced, where we used to do rigid ducting and just wrap it in lagging, an insulation layer, and tape it all up and hope it was vapor proof, it just didn't work. And we found that there was any tiny little gap in your vapor proof seal of that insulation layer, then it condensed horribly and it just ran out and actually caused some damage in some places. So once we started importing those pipes and swapping them out, that problem just went away and it's never come back. So, but they do lose energy. And so this is the reason why I brought up this slide here, which many of you will recognize as the ventilation tab out of the PHPP. And this is where we enter in the data of the ventilation system. And because you won't be able to read that, I'm just going to zoom in on a particular section, which is where we enter in how long will these pipe connections be from the ventilation unit to the thermal envelope, or the outside grills, basically. And in this case, I've just elected to pick the first ventilation unit off the rank, which apparently is 83% efficient. But you can see down here that the actual true installed efficiency comes out at 80%. So we've lost, 3%. And that is if these pipes are just 1 meter long. And what we've entered into here is that they're going to be 160 millimeters in diameter, 15 millimeters of insulation thickness, and we've done the thermal conductivity at 0.037. And so that's the kind of losses, we're going to lose 3% just by having those pipe runs to the external very, very short, just 1 meter. But just to demonstrate how things can be messed up, I've changed that same data, same pipes, same insulation layer to 20 meters long, and our true installed efficiency has gone from 83% right down to 41.8. So that's a significant loss. It's a silly number. 20 meters doesn't happen very often, but we do get requests to have, say, the ventilation unit in spot X. But for aesthetics, we want the external grills to be, 15 meters away or something like that. And this is the reason why that needs to be avoided. If you do want to, run your pipe 6 or 7 meters away, then you can do some other things. You can increase the insulation thickness. You can coat it with a reflective coating, and you can draw back some of that true installed efficiency. So what I did on the next slide is I put a 150 millimeter insulation layer over that 20 meters of ducting, and I could manage to get it back to 70.5. So, but not a good solution, and it's definitely not a solution. So the advice is minimize those losses and keep your external grills as close to the ventilation unit as you can possibly get them. And that's especially true for if we're going to run any of these pipes through, say, through roof situation. Once we get through the thermal envelope, that's literally directly above the ventilation unit. So you're probably half of a meter to the thermal envelope. But where there are unwanted gains is a pipe that's exposed to a hot roof space, even though there's 15 millimeters of insulation layer, will still pick up some heat. And quite a bit we've discovered through the years. Pretty much about a degree or a degree and a half per meter. So what we do want is the fresh air intake to be as short and direct as it possibly can be. So if it can be through the thermal envelope, straight up and out through the roof, then that's what we would recommend. Not as important for the exhaust air, so that would be the one that would step out and do something like 1 or 2 meters separation. 1.5, 2 meters separation is plenty. So now that you've seen that there's a lot of energy to be lost, even when the pipes are actually inside the thermal envelope, just imagine what the losses are or the gains are when you see a ventilation system like that. So I cringe. Moving on, this is a slide just looking at what I've just described, the hot pipes, hot roof space, pipes passing through that to the external. We had a project in Auckland where they did a retrofit, and the ventilation unit was reasonably central. It was 6.5 meters to the soffit. So we piped up and into the roof space, and we ran it to the soffit, and it was the cool shaded side, had trees around it, and everything was great. But later that summer, he contacted me and he said the house seems unusually hot. So we went around with our instruments, and it was about 30 degrees that day. And we measured the incoming air into the ventilation unit was actually about 32 degrees, or even more, I think. And so we thought, well, we're drawing air from the cool shaded side, so what's really going on? So we measured the air temperature outside, and then we measured it at the ventilation unit. And what we found was that it was picking up heat from the hot roof space. And being 6.5 meters, he'd picked up 6 degrees. So what he did was he did the 150 millimeter insulation blanket trick, and from what I understand, the problem then went away. So you can pick up a lot of energy out of a hot roof space. This image is just something I found on the internet. Just happens to be Central Otago. Somebody here may even know which house it is. The reason why I brought this slide up is just to demonstrate, the risk of drawing hot air off a sun-baked surface. There's no external grills on this one here, so nobody's picking any holes on this project. But just wanted to reiterate that if there were external grills drawing outdoor air in these locations, then the heat rises up off this cedar cladding and it just gets sucked straight into it. And it's quite dramatic. It actually has a huge impact on the air temperature. So what we're always looking for is to draw the air from around the back, around the shaded side, the southern side. And so the heat recovery efficiency of the ventilation units is typically so good that we don't have to worry about losses, but unwanted gains, they're a much bigger concern. We had a project in Auckland, which was black cedar, and that was a bit of an eye-opener, that one. The air was being drawn off actually a garden area on the shaded side, so there was lots of trees around it. And once again, unusually warm air temperatures were coming in, even in the morning. And so we went went outside, measured the air temperatures, they were fine. But when we got close to the intake air grill, it rose. And even on the shaded side of the building, we were getting 30-degree temperatures. The black cedar was 30 degrees on the shaded side at 10 a.m. On the sunny side, it was more about around 58 degrees. So if it's black cedar, it's something we have to have a look at. The other topic is keeping fan speeds low. As you've seen, that's a good idea. So this slide is really just to give a visual reference of when we set a fan speed. Basically, grills to a certain distance away will be able to achieve 30 cubic meters of air per hour, or whatever the number is that we want. We're just going to use that number today. We had a project where they want to put the unit down one end of the dwelling, and so just to demonstrate, if we did run this unit at 50%, there were so many grills up the far end that it just couldn't possibly actually produce enough pressure to be able to deliver the air volumes that we need in those spaces. So, you're kind of stuck in a situation then where you have to increase the fan speed to generate more pressure. And that's the exact opposite of what we're trying to do. So if we did just simply move the unit across to somewhere central, which there wasn't one available on this project, but just to demonstrate, then basically nearly all of the grills are easily going to be able to be serviced by that same fan speed that we couldn't do before, just because the unit was so much further down one end. So all we'd be doing is some of these grills that are close is we would be restricting the air volumes into those, and that would then therefore give us the additional pressure we need to reach the other grills. So that would be the best solution. One of the things that we have become aware of is duct lengths when we're talking about these small diameter tubes. If I go back to this previous slide, if we start talking about, say, this one here is miles away, 20 odd meters or 25 meters away, and this grill here is 5 or 6 or 7 meters away, there's obviously going to be an imbalance. One grill is going to have too much air coming out of it, and the other one is going to have not enough. So the standard approach is just simply to close down the grill and add resistance to that airflow, and that in turn will push air towards the other grill, which is further away, and that's the go-to solution. But what we've found through the years is that when a bedroom is really close, like it's 3 or 4 meters away, and you have another bedroom that's maybe 20 or 25 meters away, the difference between those is just too much. It's too much to actually think that closing down a grill is going to be a good outcome. So what happens when you close a grill down is that as you close the opening down, the velocity of the air passing through that grill increases, and velocity is actually what creates sound. So if you want a hissing grill, that's what we found through the years. We had a project in Auckland that's had very happy customers, but I think it was actually about 4 years after they moved in. I was talking to them one day. They said, "Oh, one bedroom's always noisy," and funnily enough, we actually had a whole bunch of ducting left over from their project that we'd never sold to anyone. And so the advice was, "Hey, look, can you get back in there?" It was an open roof space, and they'd run a 150 millimeter insulation blanket over the ducting. Can you get up in the roof space and just increase that duct length from 2 meters to maybe 7 or 8 or 9? So we gave them their tubes back, and that's what they did, and it actually fixed the problem. So when we're trying to slow the air volume down on a grill, this is a bit of an overlap, because best practice principles are always to keep your duct runs as short as they possibly can be, but in reality, it's the longest duct run that should be as short as it possibly can be, and that's why you want to centralize the unit. The longest duct run is what dictates what the true system pressure requirements are. So that's how fast we have to run the speed of the fan. So when we increase the length of a tube of a grill that's closer, we're not actually increasing the true system pressure, because we already have a longest duct run. That's already dictated what the true system pressure is. And so all we're doing is the same thing. If we close a grill down, we're adding resistance to the air movement, but by increasing the length of that tube, we're also doing the same thing. But what we're trying to do is we're just trying to get it to calm down before it gets to that grill, because it's just going to be over pressurized. When it comes to interior distribution, so we've got a ventilation unit, we've got noise attenuation, and then we either do the hybrid system, which is a centralized noise attenuator in the small diameter tubes, or we've got the rigid trunk and branch system. We'll just go through a couple of those. So here's just a few examples. I won't dwell on a lot of these, but there's just a few examples of what we can see as a heat recovery ventilation unit, and then the couple of silencers, or referred to sometimes as rocket launchers, and then all of the tubes disappear off into their surface cavities and make their way through. Quite a small build, this one. Here's another project in Auckland where the silencers and the distribution manifolds are remotely mounted, and that's absolutely fine. They can literally be anywhere. They can be in any orientation. They can be horizontal, vertical, upside down, back to front. It makes no difference. So the intention of those of this particular project was to bring the distribution boxes out to a more central location away from the ventilation unit, and that's absolutely fine. It's actually quite a good solution. As you can see in the next image, this is two-level dwelling, and so a lot of these tubes actually just disappear up into the level above. So they're running up through a standard internal wall cavity. If you're running, depending on which diameter tubes you're running, you may need to do a 120, 140 thick wall. But in this case, they're 75 diameter, so they can go up a standard wall cavity. Once upstairs, there's another rondo system to allow for the distribution. And what you can see on the right here is always a detail that needs conversation, is dealing with top plates and getting those tubes past your top plates. Somebody came up with a great idea, you'll see shortly. But went to a project in Karaka the other week, and so they took into consideration that you need a 150 millimeter drop, is what they elected to do on their project. But there were 5 top plates all stacked up, so they all had to be checked out to get the tubes past them into the next room. A couple of examples of rondo system running small diameter tubes, all completely inside the Intello. So obviously it should go without saying that all ducting should be entirely inside the thermal envelope. There are times when that's just not possible in deep retrofits. And so the teachings of the Passive House Institute is that anything that runs outside of the thermal envelope requires a 100 millimeter insulation layer. We tend to say 150 R3.2, and that would be a continuous uninterrupted layer of insulation blanket rolled out like carpet, not bats on top of it. The air gaps on bats is just too much. It's pretty close to a complete waste of time. So it must be an even continuous layer directly over the top. It's not a perfect solution, but it's a good solution for retrofits. We've done many projects like that. The project in the middle was in Blenheim, and it's Fairfield Construction, and it's another one of their installations also in Blenheim. So you can get a bit creative as to how you do this. The one of Fairfield Construction is rigid ducting through the office space. So they wanted the commercial look, and they wanted the unit on display. So that's how that was done. Another residence got quite creative with the pipe connections to the top and turned it into what I would consider to be a work of art. Some more examples of running tubes up inside a internal wall cavity. These are just pulled off the internet. Not quite sure actually where these were, but I see New Zealand on the back of that chap's shirt. And this is another batten system that I came across. We've got Zender 90 millimeter diameter tubes on this project. And you may be able to see in the back there that there's only a single top plate, but there's plenty of room for everything to just run completely wherever it wants to. And if that thought process can be done at the design stage, then there can be a considerable saving in man hours on the building site. So I did cover this off. How short is too short? So I won't dwell on that one again. When we move on to galvanized ducted systems or the trunk and branch system, noise attenuators are equally as important, but what we now need to consider, because we don't have a centralized noise attenuator, is attenuating what we call crosstalk between each of the rooms. And because what happens is that when you speak in one room, or you create a sound in one room, it just literally travels down the ducting and it goes into the next room. Some of the very first projects were like this, and we're exactly like that. So you could actually hear a conversation even 15 meters away. So we must put noise attenuation in between every room, and they're just called crosstalk attenuators. And the big attenuator on the left is directly after the ventilation unit. The tube ducting, as I mentioned before, is specifically for ventilation, and so it does have a smooth liner. It is antibacterial, antimicrobial, and anti-static, so dust won't stick to it. And it does have a sound absorbing quality as well. It will absorb around about half of a decibel per meter. So it's quite a nice product to work with because it's quite simple to work on a building site, running hoses instead of running engineered galvanized ducting. So here's a couple of the outcomes. If you want to maximize or minimize some of your losses of energy and gains, we're going to do short pipes to the external grills. We're going to do a central location. Fresh air grills should be on a cooler, more shaded location of the building, and always avoid hot roof spaces. Always use short pipes to the external, as I mentioned, and correct fan speed, noise attenuation, etc., etc. And that concludes my nuts and bolts workshop of heat recovery, ventilation design and installation. But here is also another document for you if you want to do any reading on the case of MVHR, which is a case study done on heat recovery, ventilation in non-airtight homes. It does make for good reading. You can actually just Google the case for MVHR and you'll probably find it. Thank you very much. Any questions? Happy to help out.
Thanks so much for that, Grant. That was fabulous. And again, I picked up some new things. So thank you very much for that. We've got lots of questions in the chat.
Yep.
Shyla, are you able to unmute people as I call out their names? So the first one is Jonathan Holmes. Jonathan, if you could read out your questions one at a time.
Oh, thanks, Grant, for such a great presentation. My first question relates to adaptability, if you like, of the mechanical ventilation system. So during the service life of a building, you might change the floor layout, you might put an extension in. Have you got any recommendations for taking those changes in use or building into account in the initial design?
Yes, definitely taking into account at the initial design stage. It's not really uncommon, to be honest. So we do have a number of projects where the future intended use will develop. And so simply we would just specify the right unit for the end use and then just make additions to the ducting or even run tubes to a location where, you know, a new connection can be made at a later date and just cap them off in the meantime. That'd be my recommendation.
Cool, thank you. My second question was, basically, I've heard two different views on the best practice in summer. So the first view that I've heard is you put the air handling unit into bypass. And the second view I've heard is that the heat exchanger is kind of like a differences engine. On one side, you've got warm, and on the other side, you've got cold. So in winter, you might have warm air going out of the building and that warmth transferring to the cooler incoming air. So flipping that around to summer, you might have cooler extract air leaving the building and warmer supply air coming into the building. So don't put the air handling unit onto bypass and have that warmth extracted from the incoming air. Wondered whether you advocated one or the other option.
Yep. So basically with a heat exchanger, it's a passive component. So it's just a static item. It's not a mechanical thing. So heat always goes to cold. So it actually does act in reverse. It's very common that AC systems are incorporated into these builds as well. So it's very common. If you're doing active cooling with your AC, your concern is losing that, but that's not the case. If it's hotter outside, what happens with a heat exchanger is that the heat always stays on the hot side. So if it's hotter outside, the heat will stay outside, and if it's hotter inside, the heat will stay inside. So it's not something you need to be too concerned about. But if you were on bypass mode, then you literally would be pumping your AC cool air outside. So that wouldn't be my recommendation. I would have it going through the heat exchanger and recovering the cold in this situation.
Cool, thank you. I wasn't going to mention who the two people I've heard those views from to save embarrassment. The last question was relating to, you mentioned keeping the duct length short as possible from the thermal envelope to the main air handling unit.
Yep.
Obviously, previously working at Fantech, the Zender products, you can specify a thicker duct, so more insulation. What do you recommend at Stiebel?
So yeah, Comfo Pipe Plus is it's 43 millimeters thick, and so we did bring some in for a project that Elron Burrell did, and but never really used it again, to be honest. It's if you're really trying to dial things in to get yourself over the line, then that's what you would do. You would increase your insulation thickness. And but what then does happen if you use a thicker diameter pipe is that your distance between centers moves out. So you have to have a special adapter to step things out. So your connections to the ventilation unit then line up with the new larger diameter pipes. So it's an excellent product. It's extremely expensive, and if the better solution is just to keep those pipes really, really short. But if it did have to be, 4 or 5 meters, then your options are increase your insulation thickness to try and cover some of that true installed efficiency. Yeah, you could do it by lagging, which would be another way. But yeah, it is the right thing to do, increasing insulation thickness.
Cheers, thank you.
So Elrond, if you can ask your question, and Shyla, can you unmute Elrond, please?
Hi there, can you hear me now? Am I unmuted?
Yes, we can hear you.
No, I can hear you.
Thanks, Grant. Funny to have a little name check there just before asking my question.
G'day. Yes, I didn't see your name coming up. So
My question was just around your comment about having the higher air changes, like maybe 0.5 air changes on average for the ventilation across a house, and somewhere like Auckland with a high humidity. In the sense of when is that a desirable thing to do? Because the risk with a higher air change rate is you bring more humidity into the house. So yes, you expel internal humidity for sure, but you bring in external humidity also.
Yeah. Yep. So the reason why I mentioned that was because a case study came up with about the FRSI levels and air exchange rates in a project in Auckland, and I'd made recommendations that they be half of an air change per hour. And when those calculations were entered into PHPP, the conclusion was actually corrected a problem. So but my personal experience, just based on comfort, is that higher ventilation volumes, I know, the theory is you're bringing in humidity from outside, but you're also, when air passes over any surface, it picks up moisture, and your clothes still dry, even when it's humid outside. So it's still removing moisture, and as long as it's not condensing on the core, it's just immediately passing straight by that and going to the outside. So it won't improve humidity, I agree, unless it's colder outside. But generally, when it's more humid, it's actually just much more comfortable as well, with higher air exchange rates.
Okay, that makes sense. Yeah, thanks for explaining.
Okay, Henrik.
Hey, howdy from Melbourne, Australia. Look, the previous questions have been answered, I think, but I have one or two more questions, if I may.
Right.
Maybe the tricky one where I really don't know the answer. Using clothes drying cupboards, using extract in small, I guess, cupboards that have a purpose for clothes drying, where wet clothes get hung in.
Yep.
Is it a good idea at all? If yes, do I need to put 2 extracts in it or increase the rate, or is it done in Australia or New Zealand?
Yeah, so it's done, and so it does come up, and drying rooms are a great idea. But what we do know is in passive houses, when you hang your clothes up, they dry anyway. Somebody was just telling me yesterday how they just hang their clothes up and they dry in one day. It's not a problem. That's a common feedback, is that bathroom towels dry even without a heated towel rail. And but drying rooms in themselves, like mud rooms and literally the drying cupboards that you mentioned, they actually don't need much ventilation volume. So the ones you can buy, say in Germany and the likes, they actually have a small element in the bottom, and then they just draw air through them, and they're very, very effective. So the air exchange rate inside the cupboard's very high, even though the volume's very low. So yeah, no, they are done. I've done a few, and but we've just done them without the element in the bottom, and they work really, really well.
Great, good feedback. Yeah. One more question about flexible ducts. What is the minimum radius? And if you go down to the very tight bend, does that impact dramatically on the flow resistance?
Yes, it does. Yep. So you always want to avoid tight bends at all costs. So you really want the most gradual, smooth bend possible. So if you're talking about the flexible 90 millimeter or 75 round pipes, so what the intention of those is, they've got a smooth liner. Obviously, they're bending, so one side of it will ukulele up, and the other side remains taut and smooth. And so as the air moves through that bend, it tends to go to the outside surface. The pressure just pushes it against the outside curve of that tube. And so it flows smoothly. But when you do an abrupt change in direction, it literally slams into it. And then that turbulence creates sound. And then you get the didgeridoo effect. And so as soon as you create sound inside a duct, it becomes even more apparent at the other end. So we're trying to minimize, that's one of the things that we're trying to minimize at all costs. If you can at all avoid tight bends, my recommendation is that you do so.
And if there's no other way, if it has to be a 90-degree sharp bend, does it need to go back to the designer like yourself to tweak the system or adjust the system, or is it on-site commissioning that needs to be fiddled a bit with?
Yeah, so it won't be a disaster, basically, is what will happen. And if there's no other solution, then it's a building site, and we just got to accept that, a building site's a live, living beast, and there's not always a solution. So it's been done a lot. Hard 90-degree bends are not uncommon, but they just should be avoided. It's always best if that tight bend is as far away from the grill as possible, so the airstream has got plenty of time to stabilize and calm down before it gets to the grill.
Good point. Oh, thanks for the feedback. Appreciate it. Yeah.
No worries.
So Tom Hughes, would you like to ask your question, please? Tom, you just need to unmute yourself.
Sorry.
Okay.
Came up as a tiny window. Thanks, Grant. It was a follow-on question around efficiency improvement with condensation forming in the core. And I just wondered if a humid climate might result in the same effect.
It does. Yeah. So air is actually a really poor medium to transfer energy. So water is considerably better at transferring energy.
Yep.
So that's what ERV is. It's recovering moisture, and that's why you can get improved energy recovery numbers if you're recovering the moisture. But in New Zealand, it's not really desirable to do that because of a number of reasons. But yeah, the more water content there is in air, the more efficient the heat recovery will be. That's true.
Okay, right. Look, other question, just haven't seen a rigid duct installation. I just wondered in terms of cost comparability with,
Yeah, typically it's a little bit cheaper. But it adds up. So normally with the galvanized ducting projects, normally they're smaller projects, like 1 or 2 bedrooms. As soon as we get to 2 levels and the likes, it's actually quite difficult to engineer a solution when you're talking about 150 millimeter diameter pipes.
Sure.
And that's the main reason why, you know, the use of these small diameter tubes has sort of become popular. In the early days, we did do rigid ducting a lot, and yeah, it was pretty hard work, I've got to say. And yeah, so yeah, generally small projects, and yes, it will be a budget solution. Yeah.
Okay. All right. Thanks.
Matthew Cutler Welsh, are you still here? No, Matthew. I couldn't see his. I think maybe he might have. He might have left already.
Might have left the room.
Yeah, he's obviously busy.
I'll answer it anyway.
Yes, please. Can you see the question?
The question is, I showed a image of a combined grill that's got exhaust air and supply air next to each other for use in tight confined spaces. Yes, there will be some cross-contamination. Will it be enough to be a problem? The answer is no. The studies I've seen on these grills, which was done by Zender in my time with them, was when they first brought out a combined grill for their smaller units. And unless there was literally no air moving over the outside surface of the building, i.e. dead calm, no air movement at all, the cross-contamination was basically zero. But when it was extremely calm and there was no air movement, the cross-contamination could be as high as 3%. And so as long as the ventilation volumes are actually adequate, then I see it as little impact, not a great concern. Councils might have a different view of that because they all have the ability to interpret regulations as they see fit. So you might get one person that has one idea on separation in one town and a different version in another town. And so what we've always done in history is we've just said, well, you know, what's the minimum commercial distance permissible? And that's 1 meter. So we've always just said, look, if you just go 1 meter, you know, no council's going to give you a problem. So, but you can put it on your plan and just see if it gets through. I don't like using them personally. I prefer grill separation. But, you know, when you need a solution, you've just got to find one. And sometimes that's it. So.
Okay. Owen, has your question been answered, or do you want to add anything to that about adding extra insulation to the ducting? Yeah, go for it. Just unmute yourself if you have anything to add. Otherwise, we'll move on to the next one.
Yep, I did cover adding additional insulation during the presentation. Yes, that is definitely one option.
Okay,
and,
so yes, this next question: what is your opinion on HRV and similar systems that use the roof space for heating, ventilation? Assuming.
What is my opinion of them? So positive pressure ventilation is, in my opinion, not the right solution for modern airtight builds. They do dry out older, less airtight homes like bungalows and villas and the likes, where there's plenty of bleed. My opinion is that, you know, any ventilation is better than no ventilation. That's the bottom line. So any ventilation is definitely better than having none at all. Just simply for removing moisture. But my biggest concern with HRV type systems is that when you pressurize a building, an example would be in winter when you're actually heating the inside of your house because it's a cold house, so you're running all your heat solutions. You are then pressurizing that air and you're pushing it out through the fabric of the building. And some of those locations like power sockets and the likes are a super highway to the external surface of your cladding, where that hot air will condense on a colder surface. And so that's the main concern, is interstitial condensation. If you want to, the best ventilation solutions, the air passes out through a fixed and controlled point. And with heat recovery ventilation, the incoming air is through a fixed controlled point, and the exhaust air is also out through a fixed controlled point. Thank you, Anonymous.
So Henrik again.
Now, all good. Thank you. All questions have been answered.
Perfect.
Great.
Okay, back to Owen.
I know I'm happy with the answers so far. Thank you.
Cool. Okay, Rafe.
Hey, Grant.
G'day, Rafe.
Hey, thanks for your talk. I've written my questions there, but I've asked you this a few times before, and Stable typically uses 75 diameter ducting, and Zender typically use 90 mil diameter.
Yep.
So quite a big sort of area difference. What's the story behind that? Why?
Okay, so the short story is that when I started with Zender and we decided to import and distribute the gear, I just literally made the decision to use 90 millimeter round instead of the other option of 75. Yep. Just purely on the basis that you could pass more air through one tube. And so really that's the short story. So one of the considerations is that so ventilation design, so you still got to take into account what are the volumes that you're going to pass through each of these tubes, and so how many connections will there be. If you're doing multiple level dwellings, like particularly 3, then it's really important to keep the velocity up inside those tubes. And so it's a bit like momentum. So air is, it's got a weight to it. So if it's moving slowly and you've got to elevate it through a number of different levels, then it tends to kind of peter out a bit. And if it's got momentum, then it can chuck itself up there and keep going. So there is a slight benefit in that. 75 millimeter round is remarkably easy to work with on a building site, and can also run up a standard internal wall cavity. So neither is a bad solution, as my advice.
Okay.
They both work really, really well. I don't see really any problem between the two, to be honest.
I guess I asked that question because sometimes the velocity of the air coming out of the grills is maybe a bit too much, and there's sometimes a little bit of noise. And I wonder if the ducts are a little bit wider at that point, slow the velocity down at the
that's what
delivery point.
So the my comments earlier on about how short is too short for your tube runs is true for all ventilation. Doesn't matter what size diameter tubes you're using, 90 or 75. If the grill that's too close is too close, then it's going to be over pressurized, and then you're relying on the grill to choke it down. And as you close the grill down, that increases the velocity at the grill, and that's a negative outcome. So if you do have grills that are too close, you just got to do that loop trick that we referred to. But you also got to make sure that those loops are really gradual, smooth bends, so the airflow remains, settled and smooth.
Sure.
So that's the real way to control velocity at the grill, is by making sure that your tube lengths are not too short.
Okay. Next question. How important is sealing access hatches for future maintenance of the ducts?
Not very. No. It's not something that we typically would worry about. So the method of cleaning them is literally a bottle brush. And but what also happens, so that's a good point actually. So what happens is basically your supply air ducts remain clean all the time. Pretty much, maybe some tiny amount of buildup over a 10-year period. But your return air ducts do pick up some grungy stuff from your home that you're trying to get out, and that does build up, and it's definitely a problem. So what's recommended is that every return air grill in the house, that you do have a coarse filter directly behind that. And that's true for all ventilation systems. It makes no difference what the brand is. And so as that gunk gathers, it's captured by that coarse filter, which is typically around about G3 rated. And it's a bit like a sock or a dunce cap. And so you take the grill out, take the sock off, you can wash it under a hot tap, you can shake it out, you can put it back in again. And the intention of that is just to help stop this crud getting into the first few meters of the ducting. So what will happen is that it'll build up. So it'll gradually get further and further down. So initially, maybe let's say after a 5-year period, you may be able to just clean the dirty section of the duct just literally with a damp cloth and a hose. Yeah, but if you did a full maintenance service, you would you'd do a wet clean of the first few meters, and then you would run the bottle brush all the way down, all the way back to the attenuators, while you've got a way of extracting air out through that. So basically vacuuming it out.
Okay, so those extract points, it's quite key to have them accessible at an accessible height. So for the homeowner, it's not, you don't need a scaffolding to sort of do that work.
No, it's not really not something I'd consider to be important for the design or the maintenance.
But if you've got those little cones that you put in.
Yes. Oh, yes. Actually, that's another really good point. All grills, whether they're supply air or return air, yeah, please put them in a location where you don't put your life at risk to access them. So that's another observation we've made through the years, is that they should be accessible. So if you've got a 4.5 meter stud height above your kitchen, don't put the grills up as high as you can get them. Yeah. So
health and safety. Yeah.
Accessibility is a good question. Yep.
Thank you.
Thanks, Rafe.
Hey, Damien, would you ask your question, please? Damien's still here, is he gone? Yep, Damien's there. Shyla, can you unmute Damien, please? Awesome, thank you.
Hi, Grant. Good presentation.
Thank you. Thank you, Damien. That's a good question you've got there too. So it's one I want to touch on.
So what happens with in a retrofit system? You showed that picture that like something out of the UK or some mid-terrace building or end-of-terrace building.
Yep.
What happens in a retrofit system? Where do you put your ducts when you don't have a service cavity? Where do you put your air handling unit?
Yep.
Can you get away with putting it in the ceiling and outside the thermal envelope, or does it all have to be?
Yep. So hot roof spaces are really aggressive environments. So I never recommend putting the actual ventilation unit in the roof. But what you can do is place the unit, somewhere inside the house, and then just bring your pipes up and into the roof. So you just have your 160 diameter EPP pipe. You'd have your noise attenuators, your rocket launchers lying on your trusses or your ceiling joists, and then you're running small diameter tubes. And so when you're doing a retrofit, you're going to lay an additional layer of insulation. So you would just run those tubes directly over the top of the existing insulation layer and fix them to those ceiling joists so that they don't sag. And then lay an additional layer of insulation blanket around about 150 millimeters thick. Now, the reason why you do that, so large diameter flexible ducting has an insulation layer that's around about 5 to 10 millimeters thick at best. And it's a massive surface area. So what we're doing by running small diameter tubes is that we are increasing the velocity of the air moving through it, and we're decreasing the surface area. So i.e. there's less surface area and there's less contact timed for energy to transfer. And by laying a 150 millimeter insulation blanket over the top instead of 5 or 10 mil, it's a remarkable difference in performance. So it's actually a fairly standard approach, is just to bring everything up into the roof space. And for a retrofit, I know that well, I've probably done 30 or 40 retrofits like that easily. So in every case, the outcome's been very, very good.
Cool, thanks. So definitely, if possible, well, definitely have the air handling unit in the thermal envelope.
Oh yeah, absolutely. Yeah. Hot, aggressive environment's not a place for a air handling unit.
Awesome, thank you.
Cool.
Okay, Tom Hughes, could you ask Grant your question, please?
I believe I've asked my question. Sorry. Yeah.
You did.
Thank you.
Actually.
Thanks, Tom.
Thanks, Tom.
Ian Scott.
Can you hear me now?
Yes.
Yeah.
Mm-hmm.
Hi, Grant. Thanks for that presentation. Hi, Jessica. Nice to see you guys. What I'd like to just clarify a little bit, you mentioned energy recovery before, and I presume it's something like the chilled kind of, I'm not sure if they're chilled beams or something. There's a chilled process in Australia where you've got a very dry climate, which doesn't require or doesn't have the same kind of moisture issues that we face here. And so they tend to use that for cooling in summer, sometimes alongside a ventilation system or an air conditioning system as well.
Yep.
Is energy recovery that sort of thing, or is it? I'm just not familiar with the product.
Yep. So energy recovery is basically, it's the same heat exchanger core. So heat is still transferring from one side to the other. But what that core will allow for is for moisture vapor to be able to pass back into the incoming airstream. So it's literally, it's moisture recovery is what it is. And so what happens is that this is possible when there's condensation forming on the core, and an ERV unit is not connected to a plumbing connection. So any of the condensate that forms inside it, it just stays there basically until it is vaporized, and then it passes back into the incoming airstream. And so the places where you get a benefit from this is in very cold climates that are very cold for a very long period of time, like 3 or 4 or 5 or 6 months of the year. And so the reason why you would want to recover moisture in those locations is that if it's say 0 degrees outside at 60% relative humidity, and you bring it in through a heat exchanger, it then warms up to about 18 degrees. Your relative humidity is going to fall to about 10%. So in those situations, it makes sense to recover moisture. So moisture is energy. Air can transfer more energy the wetter it is. So that's why they call it energy recovery, or enthalpy is the actual real term. And but in New Zealand, we're not cold enough long enough. We've got a couple of months maybe, or a month. But you really need to be like below -5 or -10 for sustained periods of time to justify doing that. The downside to ERV is that the actual true amount of heat that it recovers when there's no condensation in the core is less than a heat recovery ventilation unit. So you're compromising some of that. So ERV suitable in places like Germany, extremely hot, humid places like Taiwan and the likes, some of the upper reaches of Australia like Perth, particularly when you're using air conditioning, then those do become appropriate. But in New Zealand, all research has shown that it's just not worth it in New Zealand, so we don't bring them in at all.
And is the chillers that I'm talking about, I'm sorry, I can't think of the correct term, but they do use them in places like Melbourne, and sometimes they work, but sometimes they just add to the moisture content. It becomes very humid.
Yeah, I can't say I'm familiar with what you're referring to there, to be honest.
I'll find out the correct term and get back to you.
Yeah, and if you're talking about inline cooling in the ventilation system itself, then there's a whole bunch of technical reasons why you're going to want to avoid doing that. But as a separate air handling unit doing cooling, my recommendation always is that, you know, a separate cooling system, like an AC, is pulling air in from that location, and it's pushing the same air back out into that space, either heated up or cooled down. They work beautifully and harmoniously alongside a heat recovery ventilation system, and that will probably always be my recommendation, is to keep them entirely separate. They work harmoniously alongside each other.
Got one other question, which is something that is available in places like the United States. It's quite common, is negative pressure systems. And we're just wondering at NZGBC what sort of advice we give to people who have existing positive pressure systems, and whether they can marry that up to a negative pressure, just a continuous extract ventilation, and whether that'll help. We don't think it's going to help much in summer, but it might actually reduce moisture content in winter. What's your feeling about that?
Well, any air is better than no air, so you've got to remove the moisture. So the advantage of negative pressure ventilation systems is that the exit point is a controlled point. It's not through the fabric of the building, and that's the reason why that principle came about. The downside to it, obviously, is that you must do trickle vents somewhere else. You've got to punch some holes in the building to allow that air to come in. And then you are dealing with, you know, localized draft in bedrooms and the likes, which may or may not be, you know, appreciated.
So marrying it up to a positive pressure system instead of having trickle vents, is that a suitable combination? Running
it in reverse, is that what you're suggesting?
No. So you just obviously have to have an extract fan in your bathroom that was running continuously, so that would have to be designed properly. But assuming it was designed to kind of a negative pressure continuous ventilation system standard, would it work well with a positive pressure system?
Well, I suppose it's one way of getting balanced ventilation in there, isn't it?
Wouldn't be called a balanced ventilation system, would it?
Well, if you know the volumes of what's coming in and you know what's going out, then you can make it balanced. Yeah, that's an interesting question. Yeah, it's in theory that's all doable. You can actually, when I was with Fantech, we took a standard inline exhaust fan, and we made a hack on how we could actually control the air volume, so that you would just have a normal switch on the wall, and when you turned it on, it went to normal bathroom exhaust volume. But when you turned it off, unbeknown to the homeowner, it was still actually going at 0.35 air changes. It was quite sneaky, but it never really took off, so it didn't really get anywhere. So you can do things like that. You'd have a controlled point of air coming in through your HRV system, and you'd have a controlled volume of air going out. Yeah, so I think the theory is there. You could do that.
Need a summer bypass in the HRV system to make sure you're not drawing air from the roof space, I think.
Yeah, definitely. That would be a good idea. Draw cooler air from the most shaded location for sure. Yep. Very quickly, you'll find expense starts climbing. But yes, it's all doable in theory.
Thanks, Grant. That's great.
No worries.
Hey, Brian Butler, you've got a couple of questions.
Hello, can you hear me?
Yes. Hello, Brian.
All right. Yeah, thanks for doing this. Just a couple of quick questions on separating the intakes and exhausts.
Yeah.
Is it also advisable to consider whether one is downwind of the other, what the prevailing wind is in the region?
It won't be important. So with even with half of a meter gruel separation, your cross-contamination risk is 0. Even if there's literally a dead calm day. So that wouldn't be a problem. So if you've got another consideration would be, you know, if you've got really strong prevailing winds, then we may want to put in a windshield around that grill just so it's not over pressurized. That would be the only thing, and that has been done on a couple of projects, but it's pretty uncommon. It'd have to be very strong wind to really put that one to the test, I think. The fans will actually adjust. Sorry?
Turning the weather head so that it's actually
yeah, that's right.
Got it.
Yep. Simple solutions.
And thank you. My other question was I actually saw a few projects when we went to Germany back in, I think, 2011, where they were actually locating the supply ducts in closets for acoustic reasons. Curious what your thoughts are on that.
Yeah, not a good idea. I've seen it. I've seen people do it here in New Zealand. Yeah, I do scratch my head over that one. Yeah, it can be done. I think with good design, specifying the right unit, running at the right fan speed, doing the correct duct runs, doing nice smooth bends, nice gradual arcs in your ducting. That's how you deal with sound problems, sound pressure. I think many people have seen really badly designed and installed ventilation systems. And a friend of mine built a house in Tauranga and put one of those systems in, and we had to turn it off at night because it's just so loud, and you literally couldn't sleep in the bedroom. So basically it became 100% useless. So I can understand that some people have these concerns and they want to, do things that will combat that, but with good design and good installation, that problem shouldn't exist.
Quick follow-up to that. How do you feel about drying closets?
Really good. Yeah, I'm all for them. Yep, do an extract air and just have a nice opening down the bottom and extract air from the top. And they are very, very effective at drying clothes.
Awesome.
Yeah.
Thank you.
No worries.
Thanks, Brian. We've got about 5 more questions and we're pretty much on 2:30. So if we could just get through these as quickly as we can, that'd be awesome. And if you do have to go, please do. So David Bowden, you've got a question.
Hello.
G'day, David.
So my question was around, do you ever put flow straighteners in? Because I'm assuming what happens if you put in a 90-degree bend that you get cavitation on the trailing surface. So do you ever try to clean that out before it gets to a grill?
Because we're using small diameter tube ducts, we don't. So we don't want to, we haven't got enough room inside any of them to do that. So when I mentioned before about doing, tight 90-degree bends, my comment was make them as far away from the grill as you possibly can to allow time for that airstream to calm down and settle down. Yeah. So that would be the best practice. So yeah, not enough room for flow straighteners. It's commercial HVAC ducting does that. And
I was thinking wind tunnels. I haven't
yes,
worked in HVAC.
Yes. yeah.
Okay. Thank you.
No worries.
Awesome. And Matteo, you've got a question.
Yes, thank you. Can you hear me?
Yes.
Hi, Grant. Thanks for the presentation. I'm sure you're familiar with this because we spoke about it before. Mezzanine in a dwelling and a fit project. Would you ventilate? Would you worry too much about stratification? So would you ventilate? Would you supply air on the lower level only, or what about at the top level?
Good topic, actually. So what we get when we have a smaller footprint, like a mezzanine level upstairs and a larger footprint downstairs, is that the stacking effect is exaggerated. And so your comfort levels on the top become compromised. And so the best practice that we've found through the years is to just do return air on the top level, just actually remove that air and focus more on supply air downstairs. And because, in a dwelling, we've got fresh air coming in and we've got the stale air going out. So if, for example, it was a bedroom up there, they would probably find that they sleep better. And we could do just return air, or if it was a concern, we could say, well, we could supply air in there as well, but really, adding in return air is a good idea. That's true for not just dwellings that are just a mezzanine level, but especially when it's a mezzanine level, it tends to be 3 or 4 degrees hotter up there. And we've found, we had a project in Auckland where we had a similar scenario. They just had a master bedroom upstairs and a massive 400 square meter house downstairs. And so the heat just rose up the stairwell and it just compressed in there. And because in their design, they had a very small gym next to the bedroom. So we put a supply air grill in there, and then after they moved in, we went back and we changed it so that it was extract air at the top of the stairs, and the difference was very noticeable. I was actually surprised.
Oh, cool.
Yep.
Great to hear. Thanks.
Cool.
Jonathan, you've got another question. Has that been answered, or do you want to, is it slightly different? Jonathan Holmes.
Yeah, sort of. Grant, you mentioned that if the prevailing wind is hitting an extract grill on the outside of the building, the fans will adjust automatically. You said, does that mean that will use a lot more energy then? And would you move, if you could, the extract grill away from that prevailing wind?
Yeah, so if it's a known problem at the design stage, you would not put it there. But if it is there, the amount of additional energy that you'll use will not be much. It'll be basically unnoticeable, would be my suggestion. But so if it's, when I say it's over pressurizing, that basically means it's pushing air in there, and that'll just push past the fans. So you might have a period of time where you're kind of out of balance, and the fans will try and do what they can do to compensate for that. But generally with prevailing winds, there's quite high peaks and then quite high lows. So it's very difficult for the fan to keep up with that.
Okay, thank you.
Okay, Belen, you had a question.
Hello. Yes, I do. Hi, Grant. Hi, Jessica. Thank you.
Hello, Belen.
What are your thoughts about adding a ventilation system to a basically New Zealand building code house in Auckland? If you're doing an alteration, is that something that you would consider, or would you know how much that leakiness?
Yeah. So that article that I brought up at the end of my presentation, the case for MVHR, would be one that you should read. So just recently, so we've done quite a few projects of existing non-airtight builds and putting in heat recovery ventilation in an open roof space and running the insulation layer over those small diameter tube ducts. So it's actually not uncommon. Simon Cater at Pro Climber has just recently done it in his own home. So he's actually running a website, I believe, with all of the results, and he's busy monitoring everything. He's absolutely singing its praises like everybody else does. We had a staff member down in Christchurch who did this as well, and every single person that I've dealt with through the 13 years that has done this has always said it was a good idea.
Good idea, yes, because it also, I understand it would also help to remove humidity, like moisture in winter, and everything just gets better.
Yep, it's the actual intended purpose of heat recovery ventilation, or any ventilation, is actually the continuous removal of moisture. That's often forgotten. Improved indoor air quality is actually a byproduct of doing that, but you've got to remove the moisture, and that's why ventilation was introduced into airtight builds.
Yes, so then if this house would have like normal roof insulation, is it a big deal if you just distribute the pipes on top of the insulation layer? Like there's not going to be a thermal envelope and nothing like that. Do you think it will be a big concern if you just distribute the pipes over the insulation and that's it?
So they need to be protected from the aggressive environment. So that roof space is really aggressive. So that's why you need that additional layer of insulation, 150 millimeters thick, rolled out in one continuous layer over the top of those small diameter tubes. And so that's the only additional thing. Everything else is, done. but always without exception, you must protect those pipes from that aggressive environment.
Yes, because of your presentation. Yes, true. Cool.
Yep.
Thank you very much.
All right.
Okay, Luca.
Hi, Grant and Jessica. Thank you for the great presentation. So my question is, during the passive house course, it was mentioned that with tiny homes or minor dwellings, ventilation system can be challenging because of the closeness of the wet areas and living areas. And I just wanted to ask, what are your experiences on that, and what challenges have you faced, and what were the solutions?
Yes. So always, because you're designing cross-flow ventilation through the dwelling, you always want good grill separation. So supply air grills should always be as far away from a return air grill as possible. So yeah, you would never put a supply air grill directly outside the door of a bathroom, for example, because that air will just simply short circuit. So yeah, so every project you've got to kind of look at it and just say, well, what's a logical, accessible solution for this one? And without seeing any plans, my advice would just simply be to don't do the short circuiting thing. Don't have your supply air grill near the bathroom door. Just move it to the other end of the dwelling. So in some projects we've done a couple of small or tiny builds where there's a bedroom down one end and a bathroom down the other, and we just supply fresh air at one end and we just extract air at the other. That's all that we do.
Thank you.
No problem.
Oh, and lucky last, Owen.
I haven't really asked a question.
Yeah, so as a statement, yeah. So yeah, you can connect a condensate drain to any unit, but if it's a Zender unit, they come with a plug. If you're an ERV unit, they just plug it. So but we've actually done a few projects in the past where there's been an ERV and we've still plumbed it in anyway. One was basically in Wanaka where they were drying their clothes inside, and yeah, it was a bit of a rainforest inside the ventilation unit, so we had to get that water out somehow. So it's a bit of a hack.
But it has to be drained here in Brisbane. Humidity is too high.
Yes, yep, that would make sense. Yes, so there's an exception to every rule, so I completely agree with what you said.
Oh, well, I think that's all of our questions. Thank you so much for your participation and for really getting the most out of Grant while you've got him here. That's very sensible. We'll wrap up. Thank you all for attending, and thank you so much, Grant. That was just fabulous. I just wanted to let the people who are still here let you know that we will be getting a PHI CPD code for you, and that will be sent out to all the attendees after the webinar. And also just a heads up that the South Pacific Passive House Conference in September in Wellington will have a masterclass the day before on commissioning of ventilation systems and blower door testing, so like a passive house on site masterclass. So if you are interested in that, then keep an eye out for that, and we'll get the details out as soon as we have them. So with that, thanks again, Grant, and have a good afternoon, everybody.
Thank you. All right, see you later.